Hello everyone and welcome to Keeping Tabs on Chemistry. In this video we're going to be discussing gas laws, specifically Boyle's law, Charles' law, and the combined gas law. The units of temperature when dealing with gas laws, temperature must be in units of Kelvin for all gas laws. To remind you how to convert to Kelvin from degrees Celsius, you add 273. So why is this important? Kelvin is never a negative value, so we don't need to worry about differences on sign in two sides of an equation. Also, several gas laws use temperature in the denominator, where it's impossible to divide by zero. So absolute zero has never been physically achieved, whereas 0 degrees Celsius is common. That's 32 degrees Fahrenheit. It's the freezing point of water. So it gets rid of two mathematical problems that we don't need to deal with. So for all gas laws, we are going to be using Kelvin. Our first gas law is Boyle's law. Boyle's law defines the relationship between pressure and volume. I'll remind you guys that laws in chemistry are mathematical expressions that describe a relationship. So here I've put together a table and a graph of different pressures and volumes for the same sample of gas. And what you can notice is that at constant temperature with the same amount of gas present, as the pressure of the gas increases, the volume decreases. So you can see here as its graph, it is this kind of inverted kind of curve. This is an inverse relationship. Now we can do a bit more with this than just defining what type of relationship it has. If you look at each of these, if you multiply the two values together, 0.5 times 6 is 3, 0.6 times 5 is 3, 1 times 3 is 3, 1.5 times 2 is 3. So the data shows that any combination of pressure times volume equals a constant. We'll call it K. So P times V equals K. Now this means that one set of pressure times volume conditions must equal another set at the same temperature with the same number of moles of gas. So this is where we get the mathematical expression for Boyle's law. P1V1 equals P2V2. You'll notice this looks a lot like the dilution equation we've learned before, which was M1V1 equals M2V2. It's the same math, but now we're dealing with pressure and volume. So here's an example of Boyle's law. A sample of neon occupies a volume of 461 milliliters at STP. What will be the volume of the neon when the pressure is reduced to 93.3 kilopascals? So here you can see that we're given all units of pressure and volume. So at the beginning we have 461 milliliters. We'll call this V1. The pressure associated with it is standard pressure. And it says what will be the volume. So I'm questioning what that volume is if the pressure is reduced to 93.3 kilopascals. Now, just from what I know about pressure and volume, if I am reducing pressure, then my volume should be increasing. So I should be getting a volume greater than 461 milliliters, but I can calculate exactly what that looks like. So for my P1V1 side, STP, I'm going to put it in the same units as kilopascals here. So 101.3 kilopascals is standard pressure. The volume is 461 milliliters equals the other side 93.3 kilopascals times V2. This is my X, right? It's my variable. So when I multiply the left side and then I substitute out my variable X on the right, when I solve for that volume, I get 501 milliliters. That is greater than 461, so this makes logical sense, and that's my answer. Now the next gas law is called Charles' law. So I've done the same thing with my graph and my chart on different temperatures and volumes now. So Charles' law deals with the relationship between temperature and volume. So at constant pressure with the same amount of gas, as temperature of the gas increases, the volume is going to also increase. This is a direct relationship. Now, if we look at this and we try to multiply them together, they don't all give me the same number. But it does work if I use division instead. So the data shows that any combination of volume divided by temperature equals a constant. So now the sets equal to each other are V1 over T1 equals V2 over T2. You see, this is one of the examples where temperature is in the denominator, so I need to use Kelvin because I can't divide by 0. So here's an example. I have a 600 milliliter, okay, we'll call that V1, sample of nitrogen heated from 27 degrees Celsius to 77 degrees Celsius. Well, where I'm starting from is my initial T1, where I'm going to is my second set. And this is at constant pressure. What is the final volume? So I've labeled all of my variables. I'm going to be solving for this numerator V2. Milliliters can stay in the same unit, but degrees Celsius is a problem. I have to convert that to Kelvin. So I'm going to add 273 to each of these, and I get 300 Kelvin and 350 Kelvin. Now I can plug in. I got 600 milliliters and 300 Kelvin equals my variable V2 and then 350 Kelvin. Now, in case you're a little shaky on the algebra here, you're going to solve this by cross multiplying. So it'll be 300 times my variable x equals 600 times 350. So now when I solve for x, my second volume is 700 milliliters. Now let's take a moment to think if this makes sense. I increased temperature, which means according to Charles' law, my volume should also increase. And it did from 600 to 700. This answer makes sense. Now, the combined gas law puts Boyle's law and Charles' law together, holding only the amount or the number of moles of gas constant. So you can see with the way this is written, P1V1 over T1 equals P2V2 over T2. In the numerator, that part is the contribution from Boyle's law. And then you can see V and T is the contribution from Charles' law. So now you're dealing with 3 variables instead of just 2. Here's an example of the combined gas law. A gas takes up a volume of 17 liters, okay, V1. It has a pressure of 2.3 atmospheres, right, that's P1, and a temperature of 299 Kelvin, that's T1. Now, under my new conditions, if I raise the temperature to 350 Kelvin, that's T2, I lower the pressure to 1.5 atmospheres, P2, what is the new volume of the gas? So I now have all of my variables except for one I'm trying to solve, that V2. So I'm going to plug everything in, and you'll notice it's all in the same units, so I don't have to convert anything. So P1 was 2.3 atmospheres, V1 was 17 liters, this is 299 Kelvin, my pressure 1.5 atmospheres, my variable, and then 350 Kelvin. I'm going to cross multiply again, and I end up getting this value here. So I'm going to solve for x, and I get 30.4 liters. Now, where did I get liters from? Well, the volume that I was given on the first set of conditions was liters, so this has to be the same. That's the beauty of dealing with these gas laws. The units of pressure and volume don't matter as long as they are the same on both sides. Temperature has to be Kelvin. So now we have a graphic organizer to look at these 3 different laws and when we should be using them. So the law here is describing the mathematical equation. The graph is whether it's in the relationship for inverse versus direct, what's held constant, and the units for each of the variables. Take a moment, pause the video, try to fill it out on your own, and unpause when you're ready to go over it. Okay, we're going to start by looking at the column for Boyle's law. The law for Boyle's law is P1V1 equals P2V2. So the graph of this has pressure and volume in an inverse relationship. Now, what's held constant here is temperature and the moles or amount of gas. So we need to worry about units of pressure and volume. And for either of them, they can be any unit as long as they are the same for both sets of condition. The mathematical expression for Charles' law is V1 over T1 equals V2 over T2. This is a straight line direct relationship with temperature and volume as your units on the graph. What's held constant here is pressure and moles or amount of gas. Now the units for volume can be any as long as they're the same in each set, but the temperature must be in Kelvin. The combined gas law is P1V1 over T1 equals P2V2 over T2. There's no graph or relationship for this because there are just too many variables to consider. So the only thing held constant here is the moles of gas. The units per pressure and volume can be any as long as they're the same, but the temperature must be in Kelvin. And that concludes our lesson on gas laws. I'll see you next time.